Hey folks, this is Gavin Jones here to talk to you about something called a stack. So this is a data structure that's going to be very useful to us. So the objectives today are to describe what a stack is and the two predominant operations we can do with the stack, which are to push and pop. We'll define what those mean in a second. And then hopefully by the end of this lesson, you understand what that is. And then given a number of push and pop operations, you can sort of trace the values that are in a stack, including accounting for these two things called overflow and underflow. You can describe how a stack could be implemented on the LC3 and potentially trace an assembly language program that utilizes a stack. So let's get started. Okay, so a stack is a data structure, like I said. We're going to start with a sort of a metaphor for a stack, and which might be a vending machine. Or you can imagine like going to the like a grocery store or pharmacy, having those little springs to sort of push the products to the front of the shelf. And what that means is that we add things to this stack by pushing them from the front to the back. So you can see kind of symbolically here I'm pushing a Snickers bar onto my stack, and followed by a Pringles onto my stack, and that sort of moves the Snickers bar down one. And when I pop, I remove something from that stack, and the thing that gets removed is the thing that was most recently added to it. So I sort of add stuff front to back, and here, since Pringles was the thing that was most recently added to my stack, when I pop something, Pringles is the thing that comes off. So we can see that implemented here in the LC3 using not necessarily the spring, right, but memory locations. So somewhere in our memory are some space set aside for our stack, and so what we'll do for now, and we'll kind of see why later, is that we'll consider FDFF to be the very first spot to be loaded in our stack, and then we're going to grow upwards effectively, to lower memory values. That'll make a little more sense in a future lesson. And the only difference between these two are that whereas in our example, the items themselves kind of move as stuff is pushed onto the stack. In our case, it's copying memory values over would be really inefficient. So what we're going to do is use something called a stack pointer. So this is going to point to the address of the top item in the stack, and it will initialize it here to the value FE00, which has other memory stuff, and it's not part of the stack. So that means when our stack pointer is FE00, that our stack is empty. And so the process of pushing things onto the stack involves, in this case, we're going to load a value into R0, and then these two instructions are kind of are the two that occur to do the pushing of that item onto the stack. The first thing we do is subtract 1 from the stack pointer. So what was FE00 becomes FDFF. That's this first open spot in our stack. And then we store the value that we want. In this case, it's an R0. Store that value in the location specified by R6. So after we sort of execute these instructions, the value 17, which was an R0, is placed in FDFF, and that's the spot where the stack pointer is pointing. And then if we want to push a second item, okay, we can load something else into R0. We can execute those same two instructions, subtract 1 from the stack pointer, and then store the value in R0 to the value pointer at the stack. So now we can see that the pointer was decremented 1 more. It's pointing at FDFE, and then that is the location of where 42 is. So you can see that in this case, kind of our stack is effectively growing upwards. When we want to pull or pop an item from the stack, then we do effectively the two things in reverse. So we'll take an item out of the spot pointed to by R6 and load it into the register R0. So this value here is loaded into R0, and then we're going to add 1 to the stack. So what was FDFE now becomes FDFF, and that points to this value 17, which is now back at the top of our stack. And this little note here about 42 being garbage is just referencing the fact that there's no part of this pop operation that actually clears this memory location. So FDFE still technically contains the value 42, but it's considered to be garbage because there's no way to access it. If we try to pop another value, we'll get 17. As soon as we push a value, then things get overwritten. So that's just a kind of a note of clarification that nothing's actually clearing this thing in memory, but we are, but it is inaccessible. So there are two instances where you need to be a little cautious about using a stack, and those are mentioned previously as overflow and underflow. So you can imagine if my stack is full. So going back to the analogy of this vending machine, right? If I've got items in my vending machine that go from front to back, and I try to insert another item into that stack, there's not any feasible way to do that. So I've got somewhat of an erroneous condition here. Similarly, if I try to remove something from a stack that's empty, then I'm in sort of an underflow condition. And so if we're implementing a stack on an LC3, you can see here that the stack eventually it's going to go large enough that it'll run right up against our program memory, or whatever the maximum value we've set it to be. In which case, if we try to execute these instructions here of push an item onto the stack, well, we sort of run into some erroneous behavior. Similarly, if our stack is empty, so here our stack pointer R6 is FE00, that means there's nothing in our stack, and we try to execute these instructions to pop an item off the stack. Well, again, what should happen, right? That's an erroneous condition. In many cases, when you actually write programs for computers, it is up to the programmer or the compiler really to make sure that those two error conditions don't come about. So you might spend a lot of your time not actually sort of actively managing overflow and underflow in a stack. But by way of completeness, the book does sort of mention what should happen in those cases. So there are examples of operations that check for underflow based on some minimum value for the stack pointer, and pop operations that check for the other case. And if you go to section 8.2.4, you can see sort of the complete picture where we have push and pop operations that don't just adjust the stack but also check for these overflow and underflow conditions. And in this case, the program returns the value to indicate success or failure if based on which condition we're in. So this stack, it can be really useful, and we can see. I'll show you an example of kind of one way in which it's very useful if we consider what we just sort of learned about subroutines. So you can imagine without a stack, if I've got 4 subroutines A, B, C, and D, then each one of them might potentially need to save R0 to R7. Well, I guess R0 to R6. If they use them in the subroutine, so in sort of a worst case scenario, we're saving 8 spots in memory for every function to potentially have a place where it can store these registers. And and you might say 32 words is pretty small, but that's just 4 functions. If we have larger and larger programs, and we're wasting a lot of space dedicated to store values for these registers for functions that might only be called once. But if instead of saving those values to a specific place in memory, we just sort of reserve a stack, then as we need values, we can push them onto the stack. And so in this same scenario, we have 4 functions. They might all still potentially need to save 8 words apiece. They don't need them all at the same time. So the stack lets us, if we're calling A, then B, then A, the A function can push its, the registers it needs to save onto the stack. And then when it finishes, the stack can reclaim those values. When we get to subroutine B, B can store its values onto the stack next, but it doesn't, they're effectively the same place as the registers that A was saving are in. They're in these lower elements in the stack, but because we're in function B and not function A anymore, then we don't need to save them both at the same time. And so in this scenario, now we are only needing as much memory as sort of the largest function needs at any one point in time. We don't necessarily need to save memory for every function in our system. So this can be very beneficial because we use less memory Number one, that's important. And two, this also supports a thing called recursion, which if you pursue one of the lessons coming up, you'll see what that is and why effectively we can't do it unless we have something like a stack that can kind of expand and contract as we need space to store memories in, and then can reclaim it. So a stack, I've got a couple of notes up here to help summarize, is an abstract data type, meaning it can have multiple implementations, and the idea is that it's a LIFO data structure, meaning last in, first out. So the last item to get pushed onto the stack is the first item that gets popped off the stack when we issue the pop operation. And how we implement that on the LC3 is to reserve a section of memory for our stack, and then to co-opt R6, which becomes now our stack pointer, to point to the top element in our stack, and then we can add to the stack pointer and store value on our stack when we are pushing items onto that stack, and we can pull a value out of that spot on the stack, and then add one to the stack pointer when we are popping values off in that stack. And that when we use the stack, then this can eliminate the need for some global memory. Recall down here at the bottom that we had global memory for basically all of our functions, whereas when we were using a stack, we only needed enough memory to support whatever function we were in at the time. And it also supports recursion, which is kind of important. Okay, so the last thing I'll show you is that you highly encouraged to put the stuff in the simulator to kind of go through these examples here of pushing and popping items from the stack, or to enter some of the code examples here from the book. But I also found a stack simulator. So if you just want to kind of a quick look at how a stack would perform, then you can go to that, follow that link that's in the notes, and here if I enter values, then I can execute push and pop operations. So let's push a bunch of data onto the stack. One of the neat things about this simulator is that it handles, can handle all kinds of data types, which is kind of cool. So you can see I've pushed these values starting with 45 onto my stack. Then if I pop a value, G was the last one there, the last one I pushed on, so it was the first one out. I can pop the items in reverse order now to sort of reclaim my stack. So this can be a useful tool to sort of visualize what's going on with the stack that, if you're not fully comfortable using the LC3 assembly language just yet. All right, folks, that's all I got. I'll see you next time.